All right, so let's resume our activities for this afternoon. So I'm deeply honored and happy to introduce Professor Alessio Figalli from University of Texas at Austin. So I'll do some comments on Figalli's CV. Figalli actually finished his PhD in the Scuola Normale Superiore di Pisa and also in the École Normale Supérieure de Lyon under the supervision of Luigi Ambrosio and Cédric Villani. So after that, he passed some time in many universities. I'll mention just a couple of them. He was in Nice, and then École Polytechnique. Then he went to Austin, the University of Texas at Austin. I think it was in 2009. I met him the year before, in 2008, in the opportunity of the conference in honor to Luis. So he has many prizes and awards. So I'll mention just a couple of them. Otherwise, we would have to transfer his course for next week. So a couple of them, he was invited to the Congress, to the International Congress of Mathematicians in 2014. He was also invited to the invited speaker for the European Congress of Mathematics, ECM, in 2012. He won the European Mathematical Society Prize in 2012. He is a member of the editorial board of many important journals. So I'll mention just a couple of them, like Duke and Analysis of PDEs. And it's very impressive the range of scientific subjects that he has worked on. So I'll mention a couple of them. So free boundary problems, geometric measure theory, optimal transport, and many others. So he is considered by many of the top-notch mathematicians today as a rising star. So let me just comment. He will be doing the following up, the second part of the course that was lectured by Luigi Ambrosio last week. Luigi gave us a wonderful mini course, 4 lectures mini course on the DiPerna and Lions theory for non-smooth vector fields. So Alessio will be continue this subject today. So Alessio, on the behalf of the organizing committee, I would like to say that we are deeply honored and happy to have you here. Please.
Oh, wow. Thank you so much, Diego, for the impressive introduction. So it's a great pleasure and honor for me to be here back in Rio. I was here last year for the hyperbolic conference in IMPA, and I'm very happy to be back. So in this second, let's say, part of this course on transport equation, my focus will be more on PDEs. In fact, my goal is to try to explain how this DiPerna and Lions theory can be used to study the Vlasov-Poisson system. So this will be my goal. Now, in some sense, I want to keep this course, even if it is the second part of Luigi course of last week, kind of independent from it. So you saw already a lot of techniques last week. I will kind of rediscuss some of the topics that Luigi already talked about last week, but kind of from a different perspective, because this is the one also that is going to be more important for us in Vlasov-Poisson. So at the end, really, this course will be kind of independent from what Luigi did, but of course, a complement of it. So you can think of that as 2 independent units. So maybe let me restart summarizing what are the objects that we can play with. So it's kind of a brief summary of, as I say, the object that play in the game. So let's say I will always have a vector field, BT from Rn into Rn, T because it's a time-dependent vector field, and associated to a vector field, there are going to be 3 objects that I can assign to them. So the first thing I can consider is the ODE associated to the vector field Bt. So what you do is that you solve x dot equal Bt of capital X with initial condition, let's say. So this is the flow map, right? So what's happening is that I have t equals 0 here. I have a point x, and x dot little x is the flow. So it's the trajectory starting from little x at time 0. Then I have the continuity equation. So C for continuity. Equation. So there is the following PDE. I have the time derivative of some time-dependent measure or function, you can think of a function, plus the divergence with respect to x of Bt mu t equal to 0 with some initial condition. So mu at time 0 equal to some given measure mu bar. And then I have a third object, which is the transport equation. So T for transport equation, where with respect to the previous one, we switch the divergence and the vector field. So the equation is, this is set on functions. So I'm going to use the notation rho to express mu, to express that mu is a measure. One should think that PD for measure rho, because we think of this as applied to a function, to a density function, for instance. And here we have Bt times the gradient with respect to x of rho t equal to 0. And again, rho at time 0 is some given density rho bar. Okay, so these are the 3 objects into play, and they are strictly related. So actually, so if we are in the classical setting, where by classical I mean that if Bt is Lipschitz in space, then by Cauchy-Lipschitz, there exists a unique solution to the ODE. Right? You can always solve uniquely the ODE. You get a flow which is invertible and nice. Now, once you have this flow, so once you can solve the ODE, we can then move to the second equation, the continuity equation. So for the continuity equation, we actually have an explicit formula. So there exists a unique solution of the continuity equation, and the formula is the following. Mu t is the push forward through the flow of the initial condition. So this means the following. I'm going to try to do a picture. So we have t equals 0. Then let's say we have a different time. So this is time evolving. Let's say this is my measure mu at mu bar. And my measure mu t. So this is different time. And what this formula means the following. So if you give me any set A here, and you look how much mass mu bar gives to A, this must be equal to the mass that mu t gives to the image of A through the flow. So the flow will make the points into A evolve into a new set xt of A. This is the image of A in time. And so the mass here, which is above, must be equal to the mass that mu t gives to the image. So this is equivalent to say that mu t of x t of A is equal to mu bar of A. And so this is just a definition. And an equivalent definition is that for every test function, the integral of phi d mu t is equal to the integral of phi composed with capital X of t d mu bar. And this is actually very useful to keep in mind as a definition. So I will try, if I can do it, not to erase it. OK, what about now the transport equation? For the transport equation, we also have an explicit formula. So there exists a unique solution of the transport equation. And this is given by the formula rho t at a point x is simply rho bar at the point xt minus 1 of little x. So let me maybe draw again. T equals 0. This is a general time, let's say. So if I want to know the value of rho t at this time, at this time for this point, I just go back in time. I look from which point little x was coming from. And the value of rho t at this point is equal to the value of rho bar at this point. So this is why it's called a transport equation because the value of rho bar is transported along the flow. So this is why this is good. It's good to see this equation of functions because you have to talk about the value of the function. Doesn't make sense for measures, this. While the other formula makes much more, the other equation, the continuity equation, makes much more sense for measure just because of the formula you get. You have to take, basically, you have the mass that is in A, and you take the mass here, and you send it, whatever mass was in A, you send it to xt of A. So since you think about mass more than about the value, this makes more sense for measure, and this makes sense for functions. OK, so this is just a very quick overview. And now, from now on, I'm going to work actually with divergence-free vector fields, just because anyhow this is everything I'm going to need for my purposes. Anyhow, Vlasov-Poisson has a divergence-free vector field. So I'm going to let's assume now that the divergence of Bt is identically 0. Okay? Then this implies that the continuity equation is actually equal to the transport equation. Because if you look at the formula of divergence of Bt mu t, this is, if you do the compute the divergence of a product, this is divergence of Bt times mu t plus Bt times gradient, say, of mu t. So if the divergence is 0, you see that the formula becomes exactly the same. So now continuity equation, transport equation for divergence field vector field, they coincide. And a consequence of this is that the flow, so xt, preserves the Lebesgue measure. And equivalently, we are going to say that xt is incompressible. So there are several ways to prove this fact. Actually, one classical and simple way to do this is by just computing the Jacobian of the flow and showing that the time derivative of the Jacobian is 0. But actually, since I wrote down the formulas for the solution of continuity and transport, I have explicit formulas. I can just use that the two formulas must coincide to deduce that the volumes must be the same. So maybe let me do this. So let's prove that xt preserves the Lebesgue measure. So I'm going to take as initial condition rho bar the function 1. So in some sense, I'm taking as initial condition the Lebesgue measure, density 1. Then on the one end, so this corresponds to say that mu bar is the Lebesgue measure, right? So mu bar is a measure, so that's the Lebesgue measure. OK, so on the one end, I have that mu t is going to be equal to some density rho t dx. I'm going to write it. And then, but rho t is equal, by the formula for the transport equation, how does the density change? Rho tx is rho bar composed with the flow. So this is rho bar composed with xt minus 1. But rho bar is 1, so this is identically 1. So this tells me that the measure mu t, which is defined as rho t dx, is equal to the Lebesgue measure for every t. On the other end, I can use now, sorry, there is no bar. I can use now this, that mu t solves the continuity equation. So also this formula is true. I can use both formulas, right? So now if I take any set, so for every a, what do I have? I have that mu bar of a is equal to mu t of xt of a. So this follows by the fact that mu t solves the continuity equation. But now mu bar is the Lebesgue measure. So this is the volume of a. And also mu t is the Lebesgue measure. We just proved it here. So this is xt of a. And see, so we prove that for every set A, xt preserves its volumes. The volume doesn't change, which is exactly my claim. OK, so this proves this first property. And now I would like to discuss something that we never saw much last week, that is the blow-up of trajectories. So last week's focus was mostly about the regularity of BT. I'm going to come back to the regularity. So in some sense, we want to go, what our goal is to remove this Lipschitz condition, is to be able to work with vector fields which are as rough as possible, because in applications, we encounter this kind of vector fields. But in fact, since this vector field, like for Vlasov-Poisson, is going to be a vector field that is given by some solution to some equation, not only we are going to have the problem of the regularity of the vector field, but we also have a problem about the growth of the vector field. And we all know that even for very smooth vector fields, infinity, the solution to the ODE can blow up in finite time. Just think x dot equal x squared. So this is a super nice vector field, x squared, in one dimension. But the trajectory blows up in finite time. So there is a problem about the growth that we have to deal with also. So let me, before going to the problem of regularity, let me make some comment about the growth condition. So under which condition can we prove that there is no blow-up? I'm going to state and prove for you a theorem which is kind of a bit of the model case in this theory, just to give a bit of the idea of the techniques and in this kind of very simple setting. But before proving the theorem that I'm going to discuss in a second, let me maybe make two comments, like the classical theory. So remark one. So if BDT is globally bounded, so let's say in L infinity is bounded by constant C, then what happens, you see that the solution x dot, which is equal to BT of x, is going to be bounded by C, which implies that x of tx, so since this time derivative is bounded by C, this is bounded by the value at time 0, which is modulus of x, plus t c times t. So if the vector field is bounded, then the trajectory, of course, is bounded, can grow at most linearly, and it doesn't blow up, of course, in finite time. So this is a trivial remark, but I wanted to make it because I'm going to use it later. Second remark, another situation where there is no blow up is when if BT of x grows at most linearly. C1 plus x. Why? Because you just substitute this bound in the ODE, you get modulus of x dot less or equal than constant, 1 plus BT of x, but I can use this bound, so I get x. And now you just integrate this by Gromwall, and you get something like, I don't know, xtx is bounded by, I don't know, the initial condition, little x, I don't know, maybe you have some constant in time as well. But let's say at most it grows, probably there is 1 plus c plus modulus of x. There should be something from this t, I don't know. But you can integrate, right? You get some most exponential in time growth. The important thing, again, is that xt doesn't blow up in time. So there are two simple situations where the ODE doesn't blow up. Now I would like try to combine them in a general statement. So I'm going to do now the computation in a better way. So this is the lemma, which was already discussed in the original paper by DiPerna and Lions. So lemma, no blow up. So the lemma is the following. Let's assume that Bt satisfies the following assumption. So Bt of x over 1 plus modulus of x. So the remark 2 was, if this quantity is bounded, then we are happy. I want to make a kind of more general assumption. I'm going to assume that this function, let me introduce this notation, is the sum, can be written as the sum of a function which is L1 in time, L1 in space, plus a function which is L1 in time, L infinity in space. So let me explain this notation. So what do I mean by this? That is, there exist two functions, g and h, non-negative, such that the following holds. Okay, maybe here I will try not to erase this formula. So this is equivalent to xt push forward mu bar equal mu t. I would like for you to keep this in mind. What does it mean push forward? So there exists function g and h such that bt of x over 1 plus modulus of x is bounded by g of tx plus h of tx. So it's bounded by sum of two functions. The first one is in this space, is L1 in time, L1 in space. So this means that the integral in time, let's say 0 capital T, integral in space of g, well, g is positive, tx dx dt is finite. And the second function is L1 in time with values in infinity. So it means that you take first L infinity norm of ht in L infinity over n, and then you compute its L1 norm, and this is also finite. Okay, so I assume that my vector field can be decomposed in this way. So basically, this part, so if I didn't have g, I would basically say that this quantity is bounded. You have to think that h basically is a bounded function. But I'm saying, okay, I don't really need this to be bounded. I'm still happy as long as this quantity is globally integrable. So under this assumption, then for almost every x, the trajectory tx dx is global. So I'm on the time interval is global, let's say on 0 t, 0 capital T. Okay? Sure.
The Vlasov-Poisson flow with a confined potential, right? And a kind of parabolic unapproximate whatever. Because the vector field x refers to variable xv,
xv.
vxv, right? So
Yeah,
that
v.
condition is essentially to put a bound to the growth of the electric field, which is
Exactly, because the one on the velocity field is trivial by this condition.
right.
Exactly.
Okay. So my question is, what is the contribution of the other part? Is that
This?
yes, the
I know this is exactly the one that can control the electric field if you have enough integrability, because in general the electric field will never be bounded. That's too much. So assuming that the electric field is too bounded, it's very restrictive. So it's easier to get a kind of integrability bounds. So this is more to take care of the electric field, and this is to take care of the velocity part, because it's a bounded contribution. So being bounded doesn't mean that you are L1 and vice versa, because you are in the wall space. Not in the V, because in the V, the velocity in the x variable is V, and V is not bounded, it's linear at infinity. Yeah, then it's bounded. So it's here, but not here. So you take care of the part here, and the electric field is taken care by this, in some sense. So you do need kind of a split. In general, these are not compatible, because this is telling you something. So in some sense, this G can be a vector field which locally is not bounded, but it must kind of decay at infinity to be globally integrable. While this part tells you are globally bounded, but maybe this is not integrable at all, because maybe it's constant 1. So a constant vector field will never satisfy, or let's say a linear vector field will never satisfy this. You need this. So this is kind of taking care of two things. Some vector field which is which has some integrability, and some vector field which has some global boundedness.
And what happens if you reverse this side of +1?
There is the modulus here. I mean, the problem then is to get bounds on the electric field. That's another problem, but in some sense, these are never going to be, for most of solutions, unless you are in the framework of smooth solutions, this is never satisfied. And that's why we have to develop a more global theory for DiPerna and Lions. So this was, here I'm just discussing at the moment the classical theory of DiPerna and Lions, which is not enough for Vlasov-Poisson, because this is never going to be satisfied. But OK, I think it's anyhow interesting, the proof, just to explain how you do this. So how do we prove that the trajectories don't blow up? So you look at, so B is x dot, right? So here you have something like x dot divided by 1 plus x. We suggest the derivative of the logarithm. So d over dt of the log of 1 plus modulus of x of tx. This is basically, so this is bounded by, well, the derivative of the log, you get 1 plus x at the denominator. And then when you differentiate the numerator, you get x dot. Well, it's bounded by this. And now here I can use my assumption. So this is b. X dot is b. So this is bt of x of t little x divided by 1 plus modulus of x. And this is bounded by g and h of t capital X plus h of t x of tx. Now for the h part, it's kind of easy because I have an infinity bound. My main problem is to take care of g. And I want to show you so let's look now at this part. So I'm going to integrate this function in space and time. So I'm going to do the integral from 0, integral over Rn, integral from 0 to t of g of t capital X of tx. So dt dx. Oops. Now, by Fubini, I can exchange time and space. So this is the integral from 0 to t, integral over Rn of g of t capital X tx dx dt. OK, now we remember that the flow preserves the Lebesgue measure. So xt push forward of dx equal dx. If you start from constant density 1, you end up with constant density 1 for the continuity equation. It's basically what I proved here. Right? If you start from the initial condition dx, you come back to dx for every time. Okay, so the xt is incompressible, preserves the Lebesgue measure, and now I'm going to apply this formula with the Lebesgue measure. So for every test function of that, which tells me that this integral is equal to the integral from 0 to t, integral over Rn of g of ty dy dt. Oops. Oh. Dt. And this is just the integral of g, which by assumption is finite. So the total integral is finite. And what does this mean? So if let me put maybe a bracket here, a parenthesis. So I know that this function, the integral from 0 to t of g in dt, integrating the x is finite, a finite integral, so this must be finite almost everywhere. So this tells me that the integral from 0 to t of g of t capital X of tx dt is finite for almost every x. And this is, so let me call this information star. Now, what about h? For h is very easy because h is bounded. Well, I have this L1 L infinity assumption, so the integral from 0 to t of h of t capital X of tx in dt is bounded by the integral from 0 to t. I can put just the infinity norm of h of t dt. By assumption, this is finite too. So let me call star star. And so this tells me that, so the integral from 0 to t of this function is finite, the integral from 0 to t of this function is finite, which means that the integral from 0 to t of this function is finite. Okay, so for by star and star star for almost every x, I know that the integral from 0 to t of the modulus over d over dt of log of 1 plus modulus of x dt is finite. So let me put maybe x of t and little x. Okay, now I want to integrate these. So to be really rigorous, I should do the following. So a priori, I still don't know whether this trajectory was blowing up. So here I'm a bit informal. So what you can do is to say, okay, if this trajectory doesn't blow up, I don't have anything to prove. Otherwise, let me just integrate this inequality up to the first blow up time. So assume that, let's say, xt blows up. So this goes to infinity as t converge to some time t star. So let's assume that the trajectory is blowing up. Let me see that this is not possible. Then I'm just going to integrate the inequality. So I'm going to say, okay, infinity is greater than the integral from 0 to t star of t star of d over dt of log of 1 plus modulus of x of t little x dt. Now this is bigger if I put the modulus outside. T star, sorry. d over dt of log 1 plus modulus of x dx dt. And what is this? This is the value at time t star minus the value at time 0. So this is log of 1 plus modulus of x of t x, let's say, for t equal t star, minus log the value at time 0, but at time 0 I'm at x, 1 plus modulus of little x. So this is finite, but if x goes to infinity, this goes to infinity. So this is infinity, right? The log of, if this was blowing up, this will go to infinity as t goes to t star. And so you get infinity minus something finite is finite. So contradiction. So for every x such that this integral is finite, in fact, for every x such that the integral of that function g was finite, the function g. So for every x such that this is finite, we know that the trajectory cannot blow up. And that's the proof. Okay, so for almost every x, we have the trajectories are global. Okay. very well. So this is everything I wanted to say about the smooth vector field. So this is in the framework, let's say, of Lipschitz vector field, where we have a flow and everything is well defined. Now we would like to go to lower regularity. So, so let's start to discuss now vector fields with lower regularity. So we'll go now to rough vector fields. So for rough vector fields, basically we have to define everything. We have to see whether a flow exists and whether it is unique. So basically these are the two main issues. We don't have any more Cauchy-Lipschitz. So we are going to assume that in the sense of distribution, the divergence of BT is always identically 0. So I'm always going to work with divergence-free vector fields, just for simplicity. You could do everything I do could be done for bounded divergence, but anyhow, for the application we have in mind, everything is divergence-free. Okay, so we would like, the goal is to construct a flow for BT. So if such a flow exists, we expect it to be incompressible because we have a divergence-free vector field. So if we want some reasonable flow, we would like it to be incompressible. So I'm going to define what do I mean by flow. This was already defined last week by Luigi, but I'm going to repeat it. So let me give a definition of what is a flow for me. So in some sense here, from now on, you have to think the following. We want to work with vector fields which are Sobolev, or anyhow, they are not Lipschitz anymore. So in particular, they are only defined almost everywhere. So necessarily, our theory is going to be an almost everywhere theory. We can't say things pointwise, because not even our vector field is going to be defined pointwise. This is why everything is defined up to set of measure 0. And so even the definition, I'm going to have to take care of sets of measure 0. So what is a flow for me? I'm going to say, so a map capital X, let's say from 0t cross Rn into Rn, is a regular Lagrangian flow and I'm going to abbreviate this as RLF, regular Lagrangian flow, if the following two properties are satisfied. So the first one is the fact that the map, so for almost every x, this capital X satisfies the ODE. So for almost every x, this map satisfies the ODE in integral form. So x of t little x is equal to little x plus the integral from 0 to t of bs of x sx in ds. So I just wrote it in an integral form. Equivalently, what I'm saying is that this x dot equal b t of x, where this derivative is the derivative in the sense of distribution. So the distribution derivative of this map is bt. So you can try to cheat like with a Cantor staircase, where you have maybe the derivative is 0 almost everywhere, but your function jump. So this is telling you that when you integrate the derivative, you really get the function. So it's not so this is true almost everywhere here. But it's an inequality in the sense of distribution. So for almost every x, we have this identity. And two, we want something on the global. We want the flow to be incompressible. I'm going to put this as an assumption. So xt push forward of the Lebesgue measure is equal to the Lebesgue measure for every t. So it's not a consequence of anything. It's not like for smooth vector field. I'm going to assume that. So I'm assuming that my flow cannot compress mass. So the first remark I should make is that this definition is a good definition. It makes sense in the following, and this is what let me explain what I mean. This was also said by Luigi. Let me repeat it. So this is a good definition in the following sense. So good definition. So assume that X is a regular Lagrangian flow for a vector field Bt. Okay? So assume that I have a vector field B and capital X is a regular Lagrangian flow for it. And assume now that I have another vector field Bt tilde, which is equal to Bt almost everywhere. So I only know that the vector field coincide almost everywhere. Then X is also a regular Lagrangian flow for Bt tilde. So this is important because since we are working with sets of measure 0, if I take a vector field and replace it in a set of measure 0, I don't want the regular Lagrangian flow to change. Right? We're trying to define a theory which is consistent. So let me prove this very quickly. I'm going to kind of do in the formal way. I'm going to use this definition. So what I know, so what I want to prove is that this identity, so I know that this identity x dot equal bt of x holds with bt by assumption, because this is a regular Lagrangian flow for bt. I want to prove that it holds even if I put a tilde here. So I'm going to say, OK, let me take the integral over Rn and the integral from 0 to t of x dot of tx minus b tilde t of x of tx dt dx. What I have to prove is that this integral is 0, because this will mean that this identity is true almost everywhere. But we want to prove that this is 0. OK. Well, since this is a regular Lagrangian flow, x is a regular Lagrangian flow for b, t, I can substitute x dot equal b. So I can say that this is the integral over Rn, integral from 0 to t, of bt of capital X of tx minus bt tilde of capital X of tx dt dx. Now I apply Fubini. This is the integral from 0 to t, integral over Rn of bt of capital X of tx minus bt tilde capital X of tx, and now dx dt, so we invert the order. And now I apply the push forward definition again, using that xt is incompressible, so here I use the assumption that my flow was already incompressible. That's why that assumption was crucial, because now I know that the image of the Lebesgue measure is the Lebesgue measure. So here I get the integral from 0 to t, integral over Rn of bt of y minus bt tilde y dy dt. But now I assume that b and b tilde were equal almost everywhere, so this is 0 almost everywhere. And so the integral is 0. Okay? Which means that this is 0 almost everywhere. So this is really this solves the ODE with bt tilde. Okay, so this now is the definition, and the main question of the theory is, when do I have a regular Lagrangian flow? So we saw last week that a regular Lagrangian flow exists when the vector field is Sobolev, W11, W1p, or when the vector field is BV. Now, Luigi was able to obtain this through a construction kind of, let's say, not direct construction. What he did was to study the PDE, was to prove some property of the PDE, and then by some kind of indirect argument was able to show that the flow existed and was unique. It was using a lot of tools. It was using this superposition principle. So there were a lot of tools behind it. I want to give a different proof that anyhow is the one that works then for our approach in Vlasov-Poisson. So it's kind of a proof which works. which work in some situations which are not covered by Luigi approach. So in some sense, but it's not more general because in fact the BV case cannot be, no one has been able up to now with this proof that I'm going to show you, probably not really all of it today, but I will start today and finish tomorrow, I guess. No one has been able to treat the BV case using the argument I'm going to use today. Okay, so it allows us to solve other situations, which is, for instance, in Vlasov-Poisson, you need this proof, but not the BV case. So they are kind of complementary at the moment. There is no one which is better than the other. Okay, so the kind of theorem that we want to discuss is the following. So if you give me a vector field Bt, which is L1 in time, L infinity, L1 in space plus L1 in time, L infinity in space. So the assumption before, the assumption that ensures that the flow is global. And then if the divergence of Bt is 0, and then if one of these three holds, so we assume either, so Bt is Sobolev, W1P, P greater or equal than 1, Bt is BV, or Bt can be written as some function f of t convolution with the gradient of the Coulombian potential, so x over x to the d, right? So this is the gradient of 1 over x to the d minus 2, the Coulomb potential. So you take the gradient of this with f in L1, f in L1. So if you are so one of these holds, so if you are in one of these three situations plus these two, then there exists a unique regular Lagrangian flow. Okay? So what Luigi did last week was to treat this case of W1P and the case of BV. And he could not treat this case. There is his approach. At the moment, no one knows how to make it work for this case. The approach that I want to describe is the one which works for this and this. No one knows how to deal with this in this approach. So to be honest, I'm not going to prove exactly this because it will take me a lot of time because I will need some kind of very fine estimates from harmonic analysis. I'm going to prove the W1P case when P is strictly greater than 1. Maybe you are aware that when P is greater than 1, you are in a better setting for functional analysis. There are better estimates. P equal 1 is always a borderline case for many estimates. So I'm going to work in a simplified situation. So my goal, so this is the theorem which holds, but the goal for me is proof of theorem when Bt is W1P with P strictly greater than 1. And I'm also going to assume that Bt is globally at infinity. So it's bounded to make sure the trajectory do not explode. So of course, you could do it in this way. It becomes much more technical. So this is a simpler condition which ensures that the trajectory do not explode. So recall, when Bt is bounded, then capital X of Tx is always bounded by little x plus Ct. So at most, the trajectory can go away by a constant times t in time. Okay, so what is the kind of idea that is behind this proof? Basically, we want to construct a flow, and we would like to prove that the flow is unique. So there are two statements in this theorem. There is the existence and the uniqueness. Okay, so the kind of approach is to try to, in this setting, is to try to find an a priori estimate on the vector, on flows. So in some sense, you would say, okay, let me take very smooth vector fields infinity, and I want to understand how regular is its flow only under these assumptions. and maybe I can pass to the limit in some way. Okay, so the idea is find a priori estimates. Okay? So let me just do two very basic computations, and let's see what the issue is. So the first thing you could try to do is to say the following. So I know, so first approach, which is not going to work, is to do the following. You say, okay, x dot is bt of x, right? So I need, see if I want to, so as I said, suppose that I have smooth vector fields. For smooth vector fields, I can construct the flows. So I have the flows of smooth vector fields. Then I would like to pass to the limit. So my vector, I let my vector field pass to the limit, and I want the flow to pass to the limit. To be able to pass to the limit in the flow, I need some regularity of this flow, because otherwise, how could I do this? And so in time, this flow is very regular because the time derivative of the flow is bounded by b, which is bounded. So I know that x dot is bounded by constant. So in time, it's very regular. The problem is in space. So let's try to differentiate in space, and let's see what happens. So if I differentiate formally, I get you chain rule, grad x dot. The derivative of this is grad bt at x, grad x. Okay? Now you take the modulus, and you get the d over dt of the modulus of grad x is bounded by the modulus of grad bt at x times the modulus of grad x. Okay? Okay, now pointwise you can't control anything pointwise because you only have Sobolev bounds here. Okay, so you could try to integrate this estimate. If I integrate, so from here I could say, okay, let me integrate, so I get d over dt of the integral of grad x is bounded by the integral of grad bt at x times grad x. Okay, once you're here, in fact, you're stuck. Because if you like to do some Gromwall argument or something, you should be able to take this out in some way. And in some sense, the only reasonable way to do this is to say, okay, this is bounded by this, but this is true if you know that grad bt is bounded. So you're saying that bt is Lipschitz. So that's too much. So to be able to do this, kind of this Gromwall argument, you need some basically L infinity bound there. You can do much better. And if you only know that this function is in LP, because this is Sobolev, it's W1P, so the gradient is in LP, there is no way you can close this inequality. I can tell you. Okay, but maybe, okay, we don't know how to deal because we have this product. So I would like to get rid of this product. So what can I do? I can take this and put it down here. So I could take this and put it at the denominator. So step 2, you will say, okay, let me look now at d over dt of modulus of grad x divided by modulus of grad x. This is bounded by grad b t of x. And this is the derivative of the logarithm. So this tells me that d over dt of the integral of the log of grad x is bounded by the integral of grad bt of capital X at time t, right? But now I have the push forward condition that tells me that the measure is preserved. So this is equal to the integral of grad bt, because the push forward, right? This is like dx, and you put dy. So if, for instance, grad b is globally L1, this is finite. And you do get an a priori bound. The problem is that, I mean, what you're saying is there is a function whose logarithm is integrable. So it's not like functionally very nice, right? I mean, you're saying that it's too weak. It's not like, you already can talk about L epsilon spaces, right? LP needs p greater or equal than 1. So saying that a function to the power epsilon as finite integral already is completely useless because it doesn't pass to the limit. And logarithm is even worse. So this can be an a priori estimate just because you're not able to pass to the limit in anything like that. Logarithm is concave. You pass to the limit when you have convex function, because convex function are lower semi-continuous. Concave function are upper semi-continuous. So when you take the limit, you get the wrong inequality. But that's natural. I mean, There is no such a space, no space of function whose logarithm is L1, right? But okay, this is instructive. We like the logarithm of the gradient. So the gradient, I can't do that because I'm not able to. So in my case, the gradient is too much. I have to differentiate the flow. It means that I already know that the flow is differentiable. So I can do this as a priori estimate. But when you don't know how to bound the gradient, what you can try to do is with incremental quotients. So you say, wait, I can do with the gradient. Let's try with incremental quotient. That makes sense. Okay? And so this is really what we would like to do. So let me tell you first where I want to go. Let me see, where did I write it? Yeah, here. Okay, here now I make my claim. So, and I guess for this proof you will have to wait tomorrow. So assume that Bt in L infinity so Bt is bounded, and let's assume also that Bt is in W1P for some P greater than 1. Then, for every R positive, the integral over BR of x of t plus h minus xt. Okay, let me put the variable little x. Oh no, what is x? Sorry. Xt, x plus h. So I have to look at translation in space. Minus xt of little x in the x. This is bounded by constant. So let's say for every t in 0t times time divided by log of modulus of h. Okay? So you see, if you divide by h here and you divide by h here, you are lost. Because, of course, then as h goes to 0, this blows up. And as h goes to 0, this will converge to this. Well, OK, there is no log, but the log was there in some sense. I traded the log inside the integral with something outside the integral. Right? There I had log of the grad. Here I don't have the log inside, but I have a log in h. So you see the familiarity of the estimates. But of course, you can divide by h and take h to 0. This blows up. But this is an a priori estimate. So it tells you not that you can differentiate. You're not able to take the limit. But it tells you that your function is kind of uniformly continuous in h. It gives you a uniform continuity well measured in L1. Right? Uniform continuity for classical function would be this. It tells you that your function here as a function space is uniformly continuous. Here, you're saying this in average. Your function is in L1 is uniformly continuous. OK, so what I would like to do I still have 15 minutes. I would just like to discuss maybe how this estimate allows me to prove existence of a flow. And then we'll see. Well, I see after this how many minutes I have. But I will start anyhow the proof of this estimate tomorrow. This way I can do everything in one lecture. OK, so let me call this. So this is call this estimate star again, well, not the star of before. And let's try to see why this estimate is enough. So the now proof of existence of a regular Lagrangian flow. So pick Bt. OK, of course, remember divergence Bt is 0. So pick Bt such that divergence Bt is 0, Bt is bounded, and Bt is W1P for some P greater than 1. Consider Bt epsilon to be Bt convolution, some convolution kernel, let's say phi epsilon. OK? So we just do convolution in x. So this would be like Bt of y phi epsilon of x minus y dy. Whatever. Phi epsilon is some C infinity and compactly supported function. Okay, so I regularize my vector field by convolution in space. Now my vector field is very nice, so the flow exists just by Cauchy-Lipschitz. So let x epsilon be the flow of B epsilon t. Notice that x epsilon are incompressible. Since the divergence of B epsilon t, so the divergence of a convolution commute, of course. So this is divergence of BT convolution phi epsilon, and this is 0. So this is 0. So if you convolve divergence-free vector fields, you still get divergence-free vector fields. So I have a family of incompressible flows. And what I would like to do is just to pass to the limit. OK, so what estimates do I have? So by star, by my claim, I know that the sup in time, let's say over 0 capital T, so I am always in a finite interval, the integral over Rn, sorry, over some ball BR, yeah, these are local estimates, of x epsilon T x plus h minus x epsilon of Tx dx. This is bounded by a constant over log h. So I have a regularity in space, uniformly in epsilon, because this estimate, as we will see tomorrow, is an a priori estimate which depends only on the L infinite bound of B and on W1P norm of B. So if you convolve, everything is still bounded. The L infinite norm is preserved, and also W1P norm. So this is OK. And second, so this is the regularity in space. Also have regularity in time. So x epsilon dot is equal to L infinity is equal to the L infinite norm of B epsilon T of x epsilon. But B was bounded, so its convolution is bounded, so everything is bounded here. So I have a bounded derivative in time. So basically, my functions x epsilon, these are functions of space and time, which are uniformly continuous in space when measured in L1, and they are Lipschitz continuous in time. So I have regularity both in space and in time, uniformly. And now there is a very classical criterion. So maybe all of you know probably Ascoli-Arzelà theorem, which tells you that if you have a family of uniformly continuous functions, then they are compact in C0. Up to subsequences, they converge uniformly to a continuous function. Now there is a version of this in L1 spaces. If you have a sequence of functions which are uniformly continuous in L1, in this sense, then they are precompact in L1. So they converge to, in L1 to some function, which of course satisfy the same continuity estimate. So by, so this is like Rayleigh-Kondrakov theorem. So by compactness theorems in L1, oh my God, Kondrakov, I don't remember the spelling. I'm not sure. Okay, I should have checked the spelling, something like that. Rayleigh theorem. We know that x epsilon converge in L1 strongly in space and time to some map capital X. Okay? So we get a limit. Now the question is this limit a flow for my vector field? This may look obvious, but it's not. So, I mean, it's not difficult, but it's not completely trivial. So let me show for you why this is the case. So how do you prove that this is a flow for my vector field? There are small subtleties because my functions are not defined almost everywhere. So that's why one has to be careful. So the tendency would be just to write the ODE for x epsilon and pass to the limit, right? So the idea would be this, that I can do, would be to say, okay, x epsilon t, let's say, then maybe you integrate this in space and time, and you say x epsilon t minus x minus the integral from 0 to t of b epsilon s of x epsilon s of x ds, right? Then you integrate from 0 to t over Rn dt dx. You know that this is identically 0 because it's a flow. And now you would like to say, okay, x epsilon converge strongly. So here you will converge to capital X. Here you converge to capital X. And then you will say here you converge to B. And then you just pass to the limit and you get that the integral is still 0. There is just a small subtlety because here you have to be careful about this limit in a composition. You are composing functions almost everywhere, and this is not even continuous. So the composition is kind of tricky when you have almost everywhere stuff. So you can't really pass to the limit because you don't know that this works. So how do you deal with this? So the idea would be this, but I don't know how to make it work, so I do in the following way. So I'm going to pick some vector field b tilde, which is continuous in X. Okay? So b tilde t, which is now continuous. And now let me write the following. So I write that the integral from 0 to t, the integral over Rn. So let me see the order. How is that? Well, actually, yeah. Oh, okay, sorry. Sorry, just one thing. So this bound is true in every ball of radius r. So you can find a limit in L1 lock. So you find a limit in L1 for every ball of radius r, and then you have to glue things together. So it's not that you can find a limit directly in Rn. So you find a limit in L1 of Br, and then you take a sequence of balls bigger and bigger, some diagonal arguments. So this is in L1 lock in T and X. So locally on balls, you have the L1 convergence of the vector field. So here in the integral, we'll do the integrals on balls. Anyhow, if I prove that for every ball I solve the ODE, I pass to the limit as r goes to infinity and I solve the ODE. So I integrate 0t, I integrate from in Br, and I consider x epsilon of tx minus x minus the integral from 0 to t, and then I test it with b tilde. So b tilde s of x epsilon of sx ds dx dt. Okay? Very well. Now, what can I say? I know that this is the integral from 0 to t of the vector field. So I know that this is equal to this. Is the integral of the vector field, b epsilon. So b epsilon s of capital X epsilon of sx ds. Okay, so here I get that this integral is bounded by the integral from 0 to t, integral over Br, and then I have the modulus of the integral from 0 to little t of b epsilon s evaluated in x epsilon minus b tilde s, both evaluated at x epsilon of s of x ds. Then dx dt. Now I take the modulus inside and I do Fubini as usual. So this is bounded by the integral from 0 to t, integral from 0 to little t, I will make it even to capital T, I don't matter, and then I have the integral over Br of this. So I put the modulus inside, I get b S epsilon minus B tilde S evaluated at the x epsilon of Sx dx and then ds. And now the last integral in dt is completely useless. There is no t anymore. Okay, so now how can I bound this? So I have the ball of reducer, okay? And I have an initial point little x. And I have this trajectory. This trajectory at most, because my vector fields are bounded, at most can reach, so remember the bound, the trajectory x epsilon at time Sx at most can move by constant time little s. And S is bounded by capital T. So this is bounded by capital X, sorry, and X is in BR. So this is bounded by capital R plus constant time T. So at most this trajectory can be in this ball. Okay, so then I do the push forward. So what happens? When you do the push forward of the Lebesgue measure inside a ball, you get a new measure, which, so let me do in this way maybe. I do x epsilon t push forward of the Lebesgue measure restricted to the ball of reducer. So if I take the Lebesgue measure inside the ball of reducer and I look at its image, for sure I get a measure which is less than if I take all the Lebesgue measure. So this is bounded by x epsilon t push forward of all the Lebesgue measure, which is equal to the Lebesgue measure. So this push forward gives me a measure which is at most the Lebesgue measure. But I also know that the points where this measure can live. I know that these points cannot leave the ball of radius r plus Ct. So at most, I get that this is bounded by integral from 0 to t, integral from 0 to t, integral of b of r plus Ct, b epsilon s minus b tilde s of y dy. Then you integrate in the s, and actually the integrate dt disappears, and I can just put a capital T in front. Okay? So we're almost done. So you look at this estimate, and now you let epsilon go to 0. Now you can, because x epsilon converge in L1 to a capital X. So you pass to the limit. Converge in L1 almost everywhere. Here, this converge almost everywhere, and you are composing this with a continuous function. So if x epsilon converge almost everywhere to x, then also b tilde s of this value will converge to the composition, because now this is continuous by assumption. Okay? Just by continuity, right? This value converge pointwise to this at almost every point, so this value converge pointwise to this at almost every point. This converge, no problem, to capital X, and this converge to Bs. So what I get in the limit, I deduce that the integral from 0 to t, integral over Br of capital X of Tx minus little x minus the integral from 0 to t of B tilde S of capital X of Sx ds dx dt. This is bounded by t integral from 0 to capital T, so this is the last part, integral over Br plus Ct of Bs minus B tilde S of y dy ds. Okay. Now we are basically done. So this is one estimate. Now, what I want to prove that this is the integral of basically this is equal to this when I put my vector field. Okay, so let me do another estimate, which is very, very similar. Now I do the integral from 0 to t of Bs minus of x Sx minus the integral from 0 to t of B tilde S of capital S of xx ds. dx dt. I want to estimate this. How do you estimate? Well, you just start back from here. It's the same argument, right? I start from here. You do it without epsilon. You go here, use the push forward, pass to the limit. Well, there is no, sorry, you use the push forward and that's it. So this is bounded. It's exactly the same without epsilon by t integral from 0 to t integral over br plus ct of bs minus bs tilde dy ds. Now you put the two estimates together by triangle inequality, and what you discover is the following, that the integral over br, let me just exchange the integrals here, so I switch br and 0t, integral from 0 to t of x tx minus x minus the integral from 0 to t of bs of capital X s little x ds, and then dt dx is bounded by 2 times t, right? I just do the triangle inequality between these two. This common factor simplifies. So I get 2 times the integral from 0 to t integral b r plus ct of bs minus bs tilde of y dy ds for every vector field bs tilde continuous. Now you see that this doesn't depend on bs tilde. This does. So what is the so I can now take this infimum over all vector fields which are continuous. And of course, we all know that every function in L1 can be approximated in L1 by continuous function, for instance, by convolution. Right? So take inf in the right-hand side over all bs tilde in C0 to get that the left-hand side is 0. Okay? Which proves that this is a flow for our vector field. So this concludes the existence part. You see it's done by compactness. It relies crucially on that a priori estimate, the claim that I didn't prove. So the goal of tomorrow will be to prove that claim and then to start to discuss other consequences. So I stop for today, and thanks for the attention.